So in this lecture, we're going to talk about parallelism. That is the ability to do multiple things at the same time and how that impacts computer architecture. So we're going to start out first talking about the parallelism we've already seen so far in the course. So you'll see that we've already introduced this and what we use it for. Then we're going to talk about multi-core processors. Why do we have multi-core processors today and what are they? We're then going to talk a little bit about parallel programming. So this is going to give you an introduction to the sorts of things you have to do to make programs run in parallel. And we're going to introduce synchronization and load balancing as two problems with this. We're then going to look at some of the problems that we have with multi-core processors and using them. The first one is going to be Amdahl's law. That's the problem if not all of your program is parallel. And then we're going to look at issues with resource sharing in multi-cores and how that affects performance. We're then going to talk about some directly computer architecture related issues for parallelism. The first one is synchronization. How do we synchronize parallel things in hardware? That is, if we have two programs running at the same time, how do we synchronize them so that they don't mess up each other? We're then going to talk about cache coherency, which is how do we keep multiple parallel caches synchronized? And then finally, we're going to talk about parallelism at the instruction level. So how can we make our processors run faster by doing instructions in parallel? So let's get started by talking about the parallelism we've already seen so far in this course. So let's look at the ALU. So when we did an AND operation in the ALU, we were doing that in parallel. We had 32 AND gates, and those 32 AND gates were all processing the AND in parallel. How about the multiplier? Well, in the case of the multiplier, we saw an example where we had this parallel multiplier. We had our two inputs, the multiplicand and the multiplier, and then we had our partial product array, where we did additions and shiftings all in parallel. So this built up this very complicated circuit that we talked about before, and this circuit was so large and complicated because we were doing it in parallel. How about the pipeline? Well, we've seen this a lot of times so far. In the pipeline, we have one instruction, another, and we keep going and we fill up our pipeline. And what do we get? Well, we get here we have 5 instructions executing at the same time. So here we have 5 instructions. All of them are executing in parallel, that is at the same time on the processor. How about in the cache? Well, we took a look at a fully associative cache here, and we said we have to search the whole cache. So we can either do this sequentially, one at a time, or we can do it all in parallel. And if we do it all in parallel, we need to be able to look at the tags and the valid bits for all of the lines at the same time. So we can look at them all in parallel here. So why didn't we check each of the lines one after another when we were using this? Well, the reason here is it's too slow. We need to have our caches be really fast because the point of the cache is to access the data quickly. So if we have a large cache and have to check each line one after another, that's going to take a long time. So we want to speed up the cache by checking all of them at the same time. So that's why we have to check them all at once. How about parallelism in virtual memory? So here we had an example where we did both the TLB lookup and the cache lookup in parallel. So we used a virtual address for the cache. We got out the results. We used the virtual address to go into the TLB, and we got out the physical address. Then we compared them. So this is a physical tag and a virtual index. We compare them, and then we see if we get a hit. So by doing this in parallel, we process through the TLB and through the cache at the same time in parallel, and then we take the results together. So we have a cache being processed in parallel and the TLB being processed at the same time. So why did we want to access the cache and the TLB in parallel? Well, because it's faster. By accessing them both in parallel at the same time, we don't have to wait for one before going to the other. So we can get faster performance. So let's take a look at the parallelism we've seen so far in the course. In the ALU, we found it was faster to do 32 ANDs at the same time than trying to do 32 1-bit ANDs. We found that it's faster to do parallel multiplication than serial multiplication. In the pipeline, we found it was faster to do 5 instructions at once than to do one at a time. In the cache, it was faster to check all tags at once versus one at a time. And in the TLB, it was faster to do the cache and TLB at the same time than to do the TLB first before accessing the cache. So why do we have parallelism? Well, we do parallelism for performance. And this makes sense. So parallelism does multiple things at the same time, and if we do multiple things at the same time, we'll finish faster. But it's also much more complicated. because now we have to keep track of all those things we're doing at the same time. So how does the pipeline execute instructions in parallel if it only fetches one instruction at a time? So here's our pipeline, and we're only fetching one instruction at a time, but what you see is we've got 5 instructions together in the pipeline once they're all there. So the answer to this is the pipeline keeps the previous 4 instructions in the pipeline while executing. So the pipeline registers are keeping track of the last 4 instructions. So we only fetch one instruction at a time, but we have 4 other instructions that we've remembered in the pipeline that we keep processing. So which was easier to build, the serial multiplier or the parallel multiplier? Well, here's the serial multiplier. You can see what we've got. We've got one adder, we've got one shifter, 2 shifters, and a little bit of control. Here's our parallel multiplier. Here we've got one input, another input, and a whole bunch of adders. This is what the parallel multiplier looks like. It's a huge circuit. So the answer here is the serial multiplier was much easier to build. The serial multiplier has to do fewer things at the same time, so it's much simpler logic. But it has to take longer because you have to do them many, many times to finish.